good morning students. So next topic is we are going to discuss about mode theory. So previously we have seen what is optical fiber. So you know the structure of the optical fiber is in the form of the cylindrical waveguide. You know the optical fiber is in the form of the cylindrical waveguide. Okay. So here this is the fiber structure, and the inner part is the core. Core is covered by cladding and it is protected by buffer coating. Okay. So in previous topic we have studied about this structure of the optical fiber and the types classification, then rays and modes. Okay. So refer the previous topic, that is the optical fiber modes and configuration. And now we are going to see the mode theory. Okay. So in order to study the mode theory, so before that you must know about the optical fiber waveguide. Okay, so you know the optical fiber is in the form of the waveguide. So to understand that mechanism, okay, so that is which mechanism you want to consider the waveguide. So the structure of the waveguide is in the form of the cylindrical shape. Okay, the glass fiber. The fiber may be made up of a glass or plastic, and the structure is cylindrical. Okay, so this is the optical waveguide. So in order to analyze this, that is in order to analyze the optical power propagation mechanism, we are going for electromagnetic mode theory, and in order to analyze that we are using the Maxwell's equation. Okay, so in order to a deep understanding about the propagation of the light, you know inside the core the light is propagating based on the total internal reflection, correct? Okay, so these will be analyzed using the electromagnetic theory, that is and it may be that is you want for this analyzation you want to solve the Maxwell's equation. Okay, so Maxwell's equation. So in electromagnetic theory there are two fields, you know, electric and the magnetic field. Okay, so the two important fields are electric and magnetic field. Both are right angle to each other, that is perpendicular to the direction of propagation. You know the light waves are propagate through the z direction. Okay, it is propagating through the z direction. So coming to the Maxwell's, in order to analyze the propagation, optical power propagation, we are moving for the Maxwell's equation. Okay, so it may be analyzed in planar waveguide as well as in the planar waveguide we have seen, that is in the dielectric slab waveguide, correct? Okay, we have analyzed in previous topic as the dielectric slab waveguide. So now next is then we can see in the circular waveguide also. Okay, in the dielectric slab waveguide that is it consists of the refractive index N1. N1 is sandwiches between the dielectric material of the refractive index N2, that is the refractive index of the cladding. Okay, so we have seen that before. In order to analyze the Maxwell's, here we are going to see the Maxwell's equation. It shows that it is supporting a finite number of guided modes. Okay, we have seen the guided modes, that is the bounded modes. Okay, the waves this travels in the core region, the light rays that travels in the core region. The optical fiber waveguide, it has the infinite radiation modes. Okay, but it is not trapped in the core and it is guided by the fiber. Okay, it is guided by the fiber. So it can be shown by this Maxwell's equation only. Okay, all these modes can be shown by the Maxwell's equation analyzed only. So if you see here, the Maxwell's equation is given by del cross A is equal to minus dou B by dou T, and del cross H equal to dou D by dou T, del dot T equal to 0, and the del dot B is equal to 0. So I had solved this Maxwell's equation for this electromagnetic theory in the, that is the derivation part in the separate video. Okay, so go through that. So while solving this, you will get these values for analyzing the Maxwell's equation, that is the derivation of Maxwell's equation. I had derived all these equations in separate video, go through it. Okay, so these are the steps which is included in the Maxwell's equation. Okay, next step, that is we want to analyze the phase velocity. Vt is equal to 1 by root of mu epsilon. Okay, so this Maxwell equation, why we are going to deriving this equation in order to obtain the improved model of propagation of light. Okay, so in order to obtain the improved model of propagation of light in optical fiber, the electromagnetic wave theory is considering this Maxwell's equation. Okay, so for this we are taking the curl equations. What are the curl equation? Del cross E is equal to minus dou B by dou T, del cross H, then del dot D, del dot B. Okay, so curl equations are these two. First two are curl equation, and these two are the divergence equation. Del dot D and del dot B are the divergence equation. So what is this? Del is a vector operator. Okay, the field vectors are related by D is equal to epsilon A and B is equal to mu H. Okay, and next you want to take the curl of the equation. Okay, you want to take the curl. See, del cross, so it is a curl of the equation. Cross, while you are taking the cross, that is a curl. Okay, while you are taking the curl equations, you got this. Next you want to obtain the you want to use the vector identity. By using the vector identity, you got this value, and finally we got del square D and del square H. Okay, and next in order to find the for planar waveguide, Cartesian coordinate means x, y, z. We are dealing with x, y, z. You got this value, and for cylindrical coordinate, that is r, phi, z. Okay, so for this we get the value. It is related to this value. Okay, so now we get the basic solution. Psi is equal to psi naught e power j omega t minus k. What is omega? Omega is the angular frequency. Okay, so it is the general form of the equation. And see, next these modes can be analyzed. I said you in the starting itself, it can be analyzed in planar waveguide or cylindrical waveguide. Okay, so while analyzing in planar waveguide, so I have given you the explanation of this in a separate video. So here if you see the modes may be calculated in three different fields. M is equal to 1, 2 and 3. T1 mode and then T2, T3. So if you see here, the crossing field is 1. Okay, so the mode is 1. And here see it touches 2 points, so the mode is 2. Here the crossing field is 3. Okay, so the value of M is equal to 3. The dominant modes are propagating in the Z direction with the electric field. Okay, so it forms the rays with the mode M is equal to 1, 2 and 3. What is mode? Mode denotes the number of zeros. Okay, so it is crossing the zero pattern 1. So M is equal to 1. Here it is crossing at 2. Okay, so it is 2. It is crossing 3 values. Okay, so here the mode value is 3. Okay, so this is known as the order of the mode or mode number. Okay, order of the mode or mode number. So the modes here appeared are the bounded modes, refracted modes and the leaky modes. Okay, so the order of the mode is equal to number of field zeros across the guides. Okay, so here number of zeros, the crossing pattern. So here the M is equal to 1, M is equal to 2 and M is equal to 3. The order of the mode is also related to the ray congruence, okay, corresponding to this mode. Okay, and see here, this shows the electric field of the guided mode. It is not completely confined inside the dielectric slab. Okay, partially only it extends partially to the cladding region. Okay, it extends partially to the cladding region. So the field varies harmonically in the guided region. Okay, guiding region. So for lower order modes, the fields are tightly concentrated near the center of the slab, and only there is a little penetration into the cladding region. You see the higher order modes, the fields are distributed more towards the edges of the guide and penetrate further into the cladding region. Okay, so this is the higher order mode and this is the lower order mode. So these are the different modes. Okay, lower order mode and higher order mode, which is shown in this picture. So listen, in waveguide equation for cylindrical fiber, the electromagnetic waves are propagating along the cylindrical fiber. You know, the optical fiber or in the shape of the cylindrical waveguide. So here we are analyzing the electromagnetic waves in the cylindrical fiber. So you know the cylindrical coordinate systems are r, phi and z. Okay, it's defined with the z axis along the axis of the waveguide. So here in cylindrical waveguides bounded in 2 dimensions. Okay, that is in planar waveguide we are analyzed T and TM modes are obtained in dielectric cylinder. Okay, in dielectric cylinder. So here in cylindrical waveguide we are using T, that is transverse electric mode. So what is transverse electric mode? When E is equal to 0, the modes are called transverse electric mode. When E is equal to when H is equal to 0, then it is known as the transverse magnetic or TM modes. Okay, transverse magnetic or TM modes. Okay, these modes are results from the meridional rays. Okay, meridional rays from the that is within the guide, that is waveguide. So what is hybrid mode? Hybrid modes means it has both the electric component as well as the magnetic field component. Okay, that is HE1 then EH1 modes. Okay, so this mode values can be seen detail in the linearly polarized modes. Okay, in linearly polarized modes. So the modes in cylindrical fibers are so it can be simplified by analyzing. That is, for weakly guided approximation, what is the del value is very less than 1. Okay, so what is known as the degenerate mode? Degenerate mode means that is it is not the fundamental mode. It is a LP mode, linearly polarized mode. Okay, that is known as the degenerate mode. Okay, we will study about the linearly polarized mode. So it is the important mode. So I had explained the concept of linearly polarized mode in a separate video. So go through this. So in linearly polarized mode, the analysis, okay, so all are based on the weakly guiding approximation. So what do you mean by weakly guiding approximation? That is the relative index difference between core and cladding. That is very much less than 1. Okay, so here there are many types of mode. There is transverse electric mode, transverse magnetic mode, and hybrid mode. Hybrid mode is the combination of both electric and magnetic mode. Okay, so here all are degenerated by HV, V plus 1, then EHV minus 1. So degenerated modes are basically HV plus 1, M and EHV minus 1, M. And another one is TE0, M, TM0, M, HE2M. Okay, all are degenerated modes. Okay, so and then the derivation for the LP modes also. So here shown the intensity profiles of the different modes. So V number is calculated. X is the V number. So what is V number means? It's a normalized frequency. It is calculated using the formula V is equal to 2 pi A by lambda into numerical aperture. Okay, so it's very important for doing the problem. And next, so what are the allowed LP modes? Okay, the allowed LP modes are here. We want to analyze the J-type Bessel functions. Okay, what is this J-type Bessel function? So it is similar to the harmonic functions. Okay, it exhibits oscillatory behavior between that is it is same as that of the sinusoidal function. Okay, it can be designated for beta. It is used as the beta VM. Okay, that VM are the lowest of, or there are 4 low, that stands as electric field or lowest order mode. I said lower order modes are TVVM, TM, then EH. There is the hybrid modes. Okay, all modes are hybrid modes. That is for dielectric fiber waveguide, all modes are hybrid modes except V is equal to 0. Okay, V is equal to 0. So V is the order. And that order may be, if V is, there are 3 orders, means the V value may be 0, 1, 2. Okay, it may vary according to the order. Okay, that is V. Then M is a mode. M value is a mode. First mode or second mode. Okay, so okay, the derivation part is discussed in a separate video. So go through that.